Welcome to this video on DSB-SC Modulation, which stands for Double Sideband Suppressed Carrier. We will explore the theory, mathematics, and practical implementation of this essential communication technique. Modulation is the process of shifting an original baseband signal to a higher passband frequency. This is crucial for several reasons, including reducing antenna size, avoiding interference, and enabling multiple signals to be transmitted simultaneously through multiplexing. At the core of modulation are two components: the message signal, MT, which holds the actual, low-frequency data, and the carrier signal, CFT, a high-frequency sinusoid that acts as the transport vehicle. Modulation is achieved by mathematically multiplying these two signals. DSB-SC is defined by the complete removal of the carrier wave to maximize power efficiency, leaving only the information-bearing upper and lower sidebands. The resulting modulated signal S of t is simply m of t multiplied by the carrier's cosine function. No discrete carrier component remains in the final output. Frequency domain analysis, using the Fourier transform, reveals the exact frequency components. The modulation process shifts the message spectrum, naturally centered at 0, up to both plus and minus the carrier frequency $p_m_c$, creating the upper and lower sidebands. The underlying mechanism for this spectral shift is the product-to-sum trigonometric identity. This identity proves that multiplying two cosine signals produces both sum and difference frequencies, perfectly explaining the shift of the message spectrum to form the sideband. Bandwidth is the total frequency range a signal occupies. For DSB-SC, the bandwidth, BW, is exactly twice the original message bandwidth, B, because both sidebands are transmitted. This is a critical design factor determining channel capacity. A strict mathematical condition for DSB-SC is that the carrier frequency, $ωc$, must be significantly greater than the maximum message bandwidth, B. This is essential to prevent overlap, avoid distortion, and maintain a clear separation for proper filter design. Carrier suppression is the key advantage, yielding absolute power efficiency as 100% of the transmission power is dedicated to the information-bearing sidebands. However, a major limitation is that this efficiency requires a complex receiver architecture for coherent detection. Demodulation is the reverse process, which relies on coherent detection. This involves multiplying the received signal with a perfectly synchronized local carrier. A low-pass filter then removes the unwanted high-frequency terms, successfully recovering the original message signal. Baseband signals are the original, low-frequency raw data unsuited for long-distance physical transmission. Passband signals are the high-frequency, modulated signals, optimized for robust communication over diverse physical channels. The key difference is the raw information versus the optimized state for active transmission. DSB-SC is used in real-world communication systems, such as analog television color transmission and specialized radio systems where high power efficiency is needed. It is also a foundational technology enabling signal multiplexing, allowing multiple signals to share a single channel. In conclusion, DSB-SC modulation achieves maximum power efficiency by suppressing the carrier. This comes with a doubled bandwidth requirement and an absolute need for synchronization at the receiver to enable coherent demodulation and accurate signal recovery.